You just stay right there, and I'll come over here to these antennas, and I'll show you what I did. We have to go back to the year 1954. Some of you people weren't even born at that time. And I was out in a field up in the mountains out northeast of Campeche, California. That's about 30 miles southeast of Fort Bragg, California, where we are now. And I was trying to add two antennas together because in 1954 there was a very weak signal coming out of San Francisco, and Eureka was also a very weak signal coming out of Channel 3 in Eureka. Channel 4 and 5 was in San Francisco. The only time I could measure and work with these signals was in the morning when the air was very stratified. And so the signal followed in these stratas of air, pretty much like total internal reflection that takes place in fiber optics, for instance. Anyway, I was adding two antennas together, and I had two equal antennas. And I had an equal length of lead line going to a field strength meter. Now, a field strength meter is a meter that reads the strength of the electrical current induced into the antennas. And you could do this with your television set if you wanted, but it's not near as accurate because the television, you have to look at this picture getting stronger or snowier, more snow or less snow, to determine when you're at your maximum for nulls. So with the field strength meter, I had these two antennas right opposite each other, and we're transmitting transmission coming from this direction. And I was hitting these antennas at exactly the same identical time. And exactly the same length of leads going to my field strength meter down there. Well, I got about 30% gain on the reading of my field strength meter. By putting two equal antennas together, I thought maybe that it ought to double, but that's the way the meter read, and that was no problem for me. I picked up the one antenna, leaving the other alone, and walked forward with it. As I did that, the needle went down and down and down on the field strength meter, till let's say it got down to 0 here. In other words, that needle kept going down and down until I touched the peg. I was totally out of phase. The signal coming on that antenna was totally out of phase with the signal coming on this antenna. It come here a half wavelength earlier is what it did. So I picked the antenna up again and walked forward with it. And it come back up and up and up till, let's say I was here. Went back and forth trying to find exactly the maximum. I said, okay, the maximum is right there. And I looked, and I'd made a mark on the ground over there. And I made another mark here, and I looked, and I'd measured one wavelength. And I was real surprised. I didn't expect to do that. And I said, hey, I measured one wavelength. All I had to do then was multiply by the frequency I was working with. It came out to be the speed of light. So I went back to the center where I got my nulls where it was out of phase. I turned the antenna around like this. Now I got my maximum here and my nulls on each end. And the nulls were much cleaner to work with. We could take a field strength meter and we could go out into what's known as Todd's Point south of Fort Bragg here, and we could pick up channel 8 off of Cotto Mountain on this antenna and the field strength meters with two antennas, and the wavelength of channel 8 is 65 inches, and we could measure that 65 inches within 1/4 of an inch of accuracy. In other words, we're down to about 1/2 of 1% of the speed of light when we're measuring. It's a very accurate measure, and it's been a big help to me all through the years since then to be able to measure any frequency I want with comparison antennas. When you get into UHF, you use a yardstick and very small antennas. These antennas happen to be cut for channel 6. Every antenna would have its maximum reception if it's resonant to the frequency. And what I mean by resonance is that current is driven across here, not the electrons, but the resulting current as those electrons move was driven across here, and it just got to this end as the next field come along and going to drive it back the other way. We're talking about Ørsted's right-hand rule now, the magnetic field perpendicular to the conductor, like we saw down here. on the demonstration equipment. This current is driven back and forth on this antenna, and it has a certain speed it can travel on that antenna. And so if the antenna is the right length, it's a very efficient transfer of energy. So I'll go back here and I'll show you something else I did. I come back to my starting point, and I wondered about the speed of electrical current traveling on a lead line. So I set the antennas right opposite each other, transmission coming from this direction, and set them at a null point now, because the nulls are much easier to work with than the maximums. Because you get a 30% reading with a maximum, but where is that 30% exactly? But with a null, the needle goes down, it just touches the peg, and you know right where you are with the nulls. So I set them at a null, and I started adding lead to one of the antennas. And I just added little pieces of lead. Because back in 1954, I didn't know where I was going with all this type of information. And so I didn't want to pass up something. I wanted to make sure I didn't go by something. So I kept adding pieces of lead. And each time I added a piece of lead, the signal got better. I continued to add lead until it went back down to the next null. So it got better for a while, and then it got worse for a while, down to the null. When I went from null to null, all I had to do then to recognize the speed of the electrical current in this conductor was to measure the amount of lead I had to go from null to null. I was measuring one wavelength. And so I could determine how fast electrical current was traveling in ribbon lead, or different types of lead line. This is a ribbon lead here. It's a twin wires covered by an insulation. And I used ladder line too. But this ribbon lead, the propagation of the current in this ribbon lead was about 75% the speed of light. In the ladder line, which is two wires and has bases across it, this propagation speed of the electrical current was about 90% the speed of light. And in other ways, I've measured the speed of light with bare rods and things like that, come out about to be 95% the speed of light. So I didn't at that time know why it traveled slower in the lead, but I determined that later on that it was the insulation of the lead that was slowing the current down inside the wire. And so it was very sophisticated measurements of being able to determine these things. And when I first discovered that was back in 1954, I just put it on my notes and put it up on a shelf and didn't do anything with it for maybe about 4 or 5 years ago, which is 1993, we'll say. And I wondered about the speed, why it was slower in ribbon lead than the ladder line. And that's what I was able to determine, that it was going slower because of the insulation on the wires. So that's the way I measured the speed of light and the speed of electrical current in conductors. Anybody can do that has antennas, and a television set or a field strength meter would be helpful.